Greetings, students. It's Mr. Harrison from school. I wanted to make a quick video to walk you through how to convert from scientific notation to standard notation, and also how to convert from standard notation to scientific notation. We'll walk you through what those terms mean, what scientific notation means, and also why you should care, because it's not just we're not learning it just because it's going to be on your SOL test, which, by the way, it is not only in science, but also in math. So this is kind of a 2-for-1, because if you get this down for science, you're also doing yourself a service for math, because eventually you're going to have to do that in both. So it's a double whammy. You get like double the SOL points by doing what you need to do. So pay attention and focus, and I'll get you hopefully where you need to be here. It really isn't as hard as you might be thinking. So just a quick review here. Scientific notation is this top number. It's 2 times 10 to the 9th. That's the form of scientific notation. This down here, which is 2 billion, 2,000,000,000,000. This is standard notation. So I like to call standard notation regular, normal notation. Scientific notation, 2 times 10 to the 9th, would be like the nerdy way to write it. So the definition of scientific notation is it's simply a method of expressing numbers that are either too big or too small to be easily written in decimal form. So like the 2 billion number, or it might be 0.000000002. So either really, really big or really, really small, we use scientific notation for. All right, so for instance, astronomical distances, like the distance between the planets, the distance between the Earth and the sun, the speed of light, population of the world, the Earth's water surface, all of those are huge, huge, huge numbers. So we're going to express those in scientific notation most of the time. And then also microscopic distances, like the distance between two cells, the diameter of a mustard seed, density of oxygen, things like that. So the Earth's population is a very, very large number. Roughly 7,800,000,000. That's a lot of people. So it's kind of a pain to write 7,888,000,000,000,000. So scientific notation is 7.8 times 10 to the 9th, which is a little easier. And I'll move this over so you can see some of these examples if you haven't already looked. Some of these examples are, this is the standard notation number. This would be the scientific notation number. So 42 million. This is a negative number. It shouldn't be a negative. That's a typo, but it's 4.2 times 10 to the 7th. Now look at this one down here. 0.00001 would be written in scientific notation 1 times 10 to the negative 5. You notice that if the numbers are bigger than 1, like all of these, then they are all positive exponents, right? But once the numbers get to be less than 1, like on the right of the decimal point, like this, that is a negative exponent. That trend's going to come back for you. Let me make sure I didn't. There we go. All right, so scientific notation is all about the decimal. And I hope you know by now that if you don't see a decimal, it's just a whole number, it's implied that the decimals are right after the last number. So right now, this 2 billion number, 2,000,000,000,000 would have a decimal right behind the last 0. So you got to find the decimal first. That's it all forms around that first step of finding the decimal. All right, we found the decimal. Now you want to move it behind the first non-zero number. So if you were to look at this, I hope you would see that the first non-zero number is going to be 2, right here where this comma is. So it's originally here. The decimal is originally here. We have to move it all the way over just in front of the 2. So when we do this, we're going to count how many humps we move it over. And by the way, I know some of you learned this last year, the year before, and apparently some of your teachers have been calling it booty cheeks, which is a little bit controversial, but that's fine because we tend to remember things that are controversial. So whichever way you want to remember is fine. Humps or booty cheeks. In this presentation, we're just going to be calling them humps. So we started here. We need to get it here. So count with me. You ready? 1, 2, 3, 4, 5, 6, 7, 8, 9 humps to get it from here all the way to here. That's why it says 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 places we moved it over. You're going to have to remember that number 9. All right. Now, remember we moved the decimal from all the way over here to right on the other side of the 2 here. So we're going to take this part right here, the 2, 0, with the decimal in between them, and we're dropping it down here, 2.0. That's all we did. Just dropped it down and rewrote it. So once we count the humps, drop down the 2.0, the next thing we need to do is address what this is called, because you need to know this name. It's going to come back into play later on when we're doing stoichiometry, which is balancing chemical equations. If we get that far this year, this first number before the decimal is called a coefficient. Coefficient. I believe that's a term you use in math as well. And a coefficient can only be between 1 and 9. That might seem like a rule you need to remember, but it really isn't, because it basically you just need to remember that it can only be one single digit. So 1 is a single digit, 2 is a single digit, 3, 4, 5, 6, 7, 8, 9, all single digits. Once you get to 10, you would write it 1, 0, depending on how you view this. 1, 0, that's 2 digits, right? 10 is 2 digits. 9 is still 1 digit. So it has to be a number between 1 and 9 because it can only be a single digit. And that's called a coefficient. So you got your coefficient of 2.0. We counted our humps. Now we just have to write this thing right here, times 10. It's called the power of 10 because it represents the power of 10. So you write 2.0 times 10. 2.0 from right where we put it right here, drop it down, times 10. Then we take the number of humps that we counted and we drop that down right here to make it our exponent. Because if you're a math wizard, you know that if you multiply something or divide it by 10, you get to move the decimal over one space, one way or the other, depending on if you're multiplying or dividing. So this 9 tells us we moved it over 9 digits times 10. And that's your final answer, 2.0 times 10 to the 9th. So this is standard notation. We converted it to scientific notation. Take a deep breath. You're on your way there. Good job. Hang with me. All right. One more thing we got to do, though. Sometimes if we have a negative exponent and we need to go from, and we also have to work our way from scientific notation back to standard notation. So we have 2 more things to do here. First thing is working with a negative number. Remember, this number here, this is in standard notation, and there's a decimal right here that's kind of covered up. Excuse me. And the number would say 0.000067. Now remember, you need to have 1 digit for a coefficient, then the decimal point, then the rest of the digits. So we take this part right here. This is the first non-zero digit, and we're going to put 6.7, and we're going to drop that right down here, 6.7. Then we count how many humps we had to move it over to get the decimal point from right here where it started to between the 6 and the 7. So count with me. Are you ready? 1, 2, 3, 4, 5 spaces or 5 humps, 5 booty cheeks. Now, this is interesting because this number is really small, right? It's not like 2 billion. This is 0.000067. Really tiny number. That's why we have a negative exponent. We'll explain that in a second. So we've got 6.7. We drop down from here. We write our form for the power of 10 times 10. And we moved it 5 spaces, but this time we moved it because it was a really, really tiny number. So we actually moved the decimal point to the right 5 spaces instead of to the left. Therefore, we put a negative 5 exponent. The final answer in scientific notation will be 6.7 times 10 to the negative 5. All right, one more thing. Hang in there, guys. We got this. When you're converting from scientific notation back to standard notation, you do exactly what you did before, but backwards. So first find your exponent. In this case, it's positive 4 is your exponent. So then you drop this 2.4 right here, down here, and you're going to move your decimal. And this is positive, right? So just think about it. If we moved our decimal to the left here, we'd end up having a really tiny number, right? 0.000. But if we move it this way, we end up with a bigger number. This is a positive exponent, which indicates it's a bigger number than 1, like the 2 billion number. So we're going to move it 4 spaces to the right to make it a bigger number. Count with me. You ready? 1, 2, 3, 4. Because it said 4 up here. Now you might be thinking, well, what good does that do us? Then we got a bunch of like humps with there's nothing there. There's invisible spaces. Well, all you got to do is fill in zeros in all these humps. So we'd write 0 here, 0 here, 0 here. And when we fill it in, we moved it over all the way here and we wrote 3 zeros because to fill in the spaces from the humps. And that is going to be your final answer, 24,000. 24000. That number obviously is a bigger number than 1, which fits with our positive 4 exponent. All right, I'm going to move this up just a little bit so you can see a little better. So if anybody gets confused on this, most of the time it's due to which direction you have to move, left or right. So remember what we said. A positive number is going to be a number bigger than 1. So a positive exponent is going to be a number bigger than 1. And the opposite is true for a small number. So in a big number right here, 2 billion, that number is going to have a positive exponent. But if you think about it, to make it in scientific notation, you have to move the decimal to the left to get it here. So when you're converting from standard to scientific notation, you're going to move it left if it's positive. On the flip side, if you're same thing, converting from standard notation to scientific notation, if it's a really small number, less than 1, then you're going to move this decimal point to the right to get it between those 2 digits. So on a small number, you're going to have a negative exponent and you're moving it to the right. Now, take all that you just learned there, flip it around if you're moving it the other way. This is from scientific notation to standard notation. The previous slide said from standard notation to scientific. If you're moving it the other way, from scientific to standard, the opposite is true. If the exponent is a positive number, that means it's a bigger number than 1. Therefore, the decimal moves to the right because you'd have to move it to the right to make it a bigger number than 1. So this is going to be 26000. I wouldn't recommend doing it in your head. I've just done it a lot, so I can do that for smaller problems. On the flip side, if the exponent is negative, like this is 5.8 times 10 to the negative 6th, that means it's going to be a smaller number than 1. And if you move the decimal point to the right, that's going to make a bigger number. The only way to make it smaller is to move it this way. So it's going to be 0.000058. Again, don't do that in your head. I wouldn't recommend it. I've just done it a lot. So if you're moving from scientific to standard and it's a positive exponent, then you're moving the decimal to the right. And if you're moving from scientific to standard and it's a negative exponent, you're moving the decimal to the left. But I just like to think of, is it a bigger number than 1 or a smaller number than 1? That's how I keep track of it. All right. Great job listening. Great job hanging in there with us today. Hopefully this is a beneficial video for you. Please don't hesitate to either email or put on Canvas comments any questions you have. You can go ahead and get started on the next assignment. Good luck.